The question of what is beauty has preoccupied philosophers since ancient times. Philosophy of beauty, starting from the antiquity until the 18th century, has had a very strong opinion that beauty was objective, meaning it is a property of the object itself. So mathematical properties of objects like proportions, symmetry, balance, and other things is what made the object beautiful. It's nothing to do, in fact, with the brain. Beginning the 18th century with Enlightenment and going forward from there, the opinion has shifted, and now there is a strong feeling that subjectivity has a lot more to do with beauty. The phrase beauty is in the eye of the beholder is actually quite recent. Culture, individuality, taste are factors that will make beauty subjective. What I want to do with you today is to ask the question from the point of view of brain science. What does the brain science say on the question of objectivity and subjectivity of beauty? And I start with a theory from psychology called the Processing Fluency Theory. This theory has two main assumptions that are important here. One is that objects are different in the way that the brain processes them. Some objects are very easily processed by the brain and others are not. And the second assumption is that the more easily the brain processes the object, the more beautiful the brain will find the object. That is the two main assumptions of this theory. So examples of properties that are considered in this context are balance, symmetry, complexity, and other properties. And I will address an example so you understand how to think about the theory, and I'll pick symmetry for my example. So, you know, in art, symmetry has been very important. Here is an example from Raphael taking very strong approach to symmetry. Now, why is symmetry be important according to this theory? Is because symmetry occurs in nature and is important to us. So faces, animals, plants, fruits have a lot of symmetry in them, and therefore the brain, because of the social and biological importance of these properties, encodes symmetry. So there is a lot of symmetry processing in the brain itself. So for example, this study, the pattern in A is very symmetric. It doesn't mean anything, it's not a fruit or a face, but it's symmetric. The pattern in B is very asymmetric. And when you look at the brain, you find that there are regions of the brain that respond very strongly to symmetry. So the theory would say, well, symmetry is processed with ease by the brain, therefore we are going to like it. It's going to be beautiful. So my colleagues and I wanted to test this theory in a variety of ways. The three people beside, the two other people besides me, one is Hassan Malin. Hassan, can you raise your hand? So he's here in the audience in case you want to ask. And Ivan Correa-Herrán is the other author, took to the question of whether, in fact, you could find evidence of processing fluency theory in artists. And what we did was we took portraits from the early Renaissance, that was the initial study, and wrote a lot of equations that measure things like symmetry, balance, complexity, and other properties, and then measured them in portraits of the early Renaissance, comparing to other kinds of images. And the first result is actually that, in fact, we find evidence that the processing fluency theory can account for artist tendencies. So I'll give you an example here. This is a measure of symmetry. We have other examples. Actually, the graph shows asymmetry, and so symmetry is downward. The being in red is measurements of symmetry in portraits of the early Renaissance by master painters. And you compare this to the bean in green or yellow, which is actually spontaneously made portraits, pictures that you take in spontaneous moments. And as you see, portraits made by master artists tend to be symmetrized. They make a special effort. It's not just taking a scene at random, but they tend to symmetrize the image. Now, the blue shows another lesson, which is that they could actually make it more symmetric. There is a way to make portraits so that the face is very frontal, the body is illuminated very homogeneously, and you can achieve even more symmetry than the artist did. And one question we ask is, why did the artist not maximize symmetry if the processing fluency theory is correct? And the second result that we obtain is that artists actually exhibit individuality. We all know this. But when they weight these various static variables, balance, symmetry, complexity. So let me show you an example. So this is a series, 3 painters from the Renaissance, and each dot there is actually a painting, and that measures the degree of imbalance and the degree of complexity in the painting. And what you find is that different painters reside in different portions of a space that we call the neurostatic space, which is where those variables reside. So for example, Antonello da Messina, the one in blue, is lower, has less complexity than the other painters. And if you take Andrea del Castagno, which is in green over there, is actually more balanced than Pedro Berruguete painted. And they each reside in a portion of the space. So there is a lot of individuality. And what we wanted to know next is, where does this individuality come from? And this is the second part, which is we are going to claim that individuality comes from learning, a learning of static values that the brain does. So how does the brain learn static values? So the first thing to know is that there are actually a relatively small number of areas in the brain that participate in a static appraisal. There are many areas of the brain are active when you see a painting, but only a few areas participate. And here is an example. There are lots of, in this study, there are lots of brains, lots of studies, lots of MRIs in different modalities, sight, sound, taste, and smell. We always with the same question: do you like this? Do you find it interesting, beautiful, and so on? And it turns out that about 4 or 3 areas of the brain are always there, and they are the areas that are marked by the rectangles in the internal circle. Now, why are those areas interesting is because they represent certain processing of information that the brain does. So sensory information, of course, is important if you're going to see a painting or hear music. Motivation, which is you're willing to act on the painting, and learning. Learning of value is very important. So now the question is, how do these 3 characteristical areas of the brain interact? And what we did is we, again, build a model, build a theory for how these variables interact, and put that in the computer and run the simulation to try to learn. And this, again, is work by Hassan Alim, who's sitting there, Correa, and I. Now, theories could be wrong, and so I love to quote Muhammad Ali on this, that I don't always know what I'm talking about, but I know I'm right. And so take my word for now. So here is how the theory works. In this theory, there are societies. In every society, there are individuals. And every individual is exposed to a few things that are related to these parts of the brains I showed you before. You are exposed to sensorial inputs. Each one of us have different motivations, hunger, sex drive, wanting to risk. And then in your society, you get rewards for certain actions that you take. Now, let me give you an example. Imagine you are seeing an apple. So the apple is in front of you, and the first thing you want to decide is if you're going to eat the apple. So from the statistics of the apple, you say, this color and shape indicates that it has, I don't know, sugar and vitamins and maybe calories and so on. Now, is it correct, your estimation of the apple? So what you do is you try the apple, and if the apple is what you predicted, you get the same reward as what you predicted or what you estimated. Now, you might or not try the apple because you may be hungry or not. Your motivation becomes a factor, so this is part of the calculation. Now, you compare the apple with your prediction, and if the prediction is right, it's fine, but if the prediction is wrong, you have to change your model for the apple. Now, imagine that you see an apple in a painting, not in front of you, but in a painting. Now, you can estimate the value, but you cannot eat the painting. And so that's what we call the static value. It's something in the painting that is going to tickle the same processes that are valuable for you in life. Now we put these things in a computer model and process them, and I'm going to show you 3 results. The result number 4 in this study is that static values compete during life, during co-learning. So here is the example. So what you do is you start, imagine that you have 2 of these variables, balance and complexity in this example. You start at 0, 0, meaning they have no value. You start being exposed to images and to rewards, and your value increases for both. But at a certain point, you can see for this individual, you start losing balance and gaining in complexity, meaning this individual values complexity more than balance for his particular static space. Now, that's an individual thing we know because we are modulated by motivation. So in this particular example, we are taking risk-taking as examples of motivation. So the thing in green are individual that is high risk-taker, the blue is risk-averse, and the middle red is risk-neutral. So if you do the simulation for an individual that is high risk-taking, the individual tends to progress and then like complexity, because complexity are things that you don't really understand very well. If you are risk-neutral, you progress through life, and eventually there is an equilibrium between balance and complexity. But if you are risk-averse, actually balance wins out. You can see the graph start rising, and then balance increases and complexity decreases. So you'd end up in different portions of the space, depending on your motivations in life. Here is an example of possibly why these artists ended in different portions of the space, because of their internal motivation as developing as artists. Finally, if you provide different rewards to, socially rewards to the individuals, they will end up in different portions of the space. And so in this example, is societal pressures. The number, so I'm not going to tell you exactly how this is done, but the number on the top that you see is changing, is different parameters of societal rewards. And as you see, as the numbers change, the individuals as a whole change in what they prefer in terms of balance and complexity. So let me finish and summarize for you what actually we learned. So first of all, the main question raised by the philosophers is beauty objective or subjective? What we learned from the brain is the following. First of all, beauty is objective because evolution, for example, in the example of symmetry that we saw, puts in the brain areas that care about those properties. They are very important for us, and therefore we become fluent in these properties and therefore like these properties in terms of beauty. But at the same time, the brain has to adjust to cultures, for example, which are different in different places. And so learning, the process of value learning and motivation become in part of the brain, and you end up with subjectivity in this case. So the philosophers from before the 18th century were right, and the philosophers from after the 18th century were also right. And both properties are there, and they are important for the biological function of the brain. Thank you.